Aaron Labdon is a PhD student in astrophysics at the University of Exeter, and he's going to talk to us about imaging the birth sites of planet formation.
Hello, yes, thank you for the introduction. This is basically my PhD project I've been working on for the past 3 years. So imaging the birth sites of planet formation. Who am I briefly? I'm originally from South Yorkshire. Did my undergrad at Aberystwyth University in Wales. That's where I came out in 2013 as pansexual, thanks to a good group of people there. And now I'm a final year PhD student in astrophysics at the University of Exeter. I'm nearly done with my studies here, so it's getting towards crunch time for my write-up at the moment. So my PhD comes under the broad umbrella of planet formation, which is the study of how we go from a giant cloud of dust and gas in space to the planet that we live on today, with all of its life, its water, its rocks, its sand and everything. So my PhD is just a small part of the puzzle of how we got to where we are today. And if we want to understand planet formation, we really need to take a step back and look at star formation first. You can't have planets without having a star. So most things in the universe start out life in what we call molecular clouds. These are giant clouds of gas in space, often many, many light years, maybe hundreds of light years across. And this is what we're showing here is a simulation by a professor here in Exeter of one of these giant molecular clouds. So the different colours represent the varying densities within this cloud. So the brighter the colour, the higher the density region. And you can see it's not a uniform distribution of gas. We've got these high dense filaments, and we've also got low density, almost void-like regions in this cloud as well. So if we start this simulation moving, you see it's not just a static cloud, but it's actually moving and churning, and you can see the denser regions are actually starting to collapse under their own gravity. Material is being pulled in towards these denser regions. If I just pause it there. And as these regions get denser, they also get the pressure increases, and so the temperature starts to increase as well. And as things get hotter and hotter, eventually you have enough matter that you can start hydrogen burning, and you end up with what we call a protostar, or just a baby newborn star in this cloud. So if we let the simulation run for another 100,000 years or so, you can see these white, dense, hot blobs start to shoot out from the denser regions of this cloud. And these are the stars that are being born inside this simulation. If we let it run to completion, we end up with about 200 stars being made in this one computation. But you can see it's not just stars we have. There's a lot of stuff left over. There's a lot of extra gas that's not being transported or transformed into stars directly. And this is the stuff that the planets will be made of. So if we take a closer look at one of the stars, one star, so initially in the early stages, there's a big halo of dust and gas surrounding these stars in a big ball. And over time, because of the rotation of the star, the material is dragged downwards into a central plane around the equator of the star, because the centrifugal forces are strongest at the equator because of the spinning, because of the rotation of the star. Material is dragged downwards and inwards, and we end up with a very flat, very thin disk around the star. And this is what we call a protoplanetary disk. And it's this thin disk which explains what we see in the solar system. So on the diagram on the right, it's fairly representative. You can see that all the planets lie mostly in the same plane. There's no planet orbiting at 90 degrees like this comet is here. All the planets are in the same plane because they formed out of the same thin disk around the sun. So how do we get to an actual planet from these thinner disks? Well, we have to take a look at the dust grains. So in these disks, about 99% of the material is just gas, mostly hydrogen, helium, a few other heavier gases. Only about 1% of the mass is actually dust. And this dust is really, really tiny. It's probably less than a micron in diameter, well away from the planet-size objects that we know about. And this dust is just sort of milling about as it orbits the star. It's got some very crude animations, just dust randomly moving about, randomly scattering. But occasionally, two dust grains collide in such a way that they stick together. Now, the chances of them actually sticking together are very small. They could collide and shatter into even smaller particles. They could just bounce away. They could do many things, but sometimes they stick together. And over many millions of years, more and more of these particles stick together, and they build up and up very slowly into larger and larger objects. And eventually we can get sort of kilometer-sized objects, which we call planetesimals, or baby planets, if you like. And there are lots of these planetesimals in our own solar system. They're in the form of asteroids, such as in the asteroid belt between Jupiter and Mars is made of many, many thousands of these planetesimal-sized objects. Yeah. But once they reach kilometer size, they really start to pick up pace. Because once you've got an object that's big enough and heavy enough, it has strong enough gravitational pull that it can start to pull in everything else around it. So as it moves through the disk as it orbits the star, and it just pulls in all the extra gas and dust that surrounds the star. And at this point, the process really starts to speed up. It's a real snowballing effect as it accumulates mass much, much quicker. And this is how you build up to the much larger scales, planetary size bodies from planetesimal size objects. You build up planets the size of Earth, the size of Jupiter in this way. But actually observing these objects becomes very tricky. If you've got a newly born planet, even if it's the size of Jupiter, a large planet, it's still going to be very, very dim, and it's a long way away around a distant star. So trying to observe it with a telescope is almost impossible, particularly if it's still surrounded by lots of dust and gas from its original disk. It's just going to be impossible to see it, even with the most powerful telescopes. But what we can see is the effects the planet has on the disk around it. So this is an image of a real protoplanetary disk. This is a real image. At the center of this, there will be a large star. It's been subtracted from the image to improve the contrast a bit that we're looking at here. And you can see this disk has been warped into a beautiful spiral arm pattern. We've got two great spiral arms around it. Almost reminds you of a galaxy looking at it. But these are probably caused by planets. If there is a large planet in here, it will be dragging material around. It will be carving out these gaps that we see, and it will be creating these beautiful sculptures that we see in the disks. And it's not just spiral arms that we see. We also see gaps in these disks, and gaps and rings. So this is a very famous image, one of the first of its kind, showing these beautiful concentric rings within the disk. And it's theorized there are several planets within the system. And as these planets are going round the central star, they're carving out a gap. Material is being attracted towards these planets, creating these gaps that we see. And then more recently, so this is a picture by my supervisor from a couple of years ago, and they reckon in this image there's a planet around this location, if you can see my mouse, and as it is orbiting around the star, it is dragging this huge arc of material behind it that's trapped in the wake of the moving planet. And so even though we can never see these actual planets, they're far too dim, we know they're there because we can see the effects that they're having on the disk. And we can start to work out some of the fundamental parameters. How heavy are these planets? How fast are they moving around the star? And we can start to test our models of planet formation, start to work out, okay, how did this planet get to where it is? And we can relate that back to our own solar system. How did our own solar system come to be from this? But the trouble is, it's not always easy to make an image like this. In fact, it's very difficult indeed to make an image like this. So on the left here, we've got currently the largest telescope in the world. This is on Gran Canaria, and it's about just over 10 meters in diameter. So it's a pretty big telescope. And on the right here, we've got what's called, imaginatively, the extremely large telescope. Now this is currently under construction, but when it's finished in the Atacama Desert in Chile, it will be 40 meters in diameter, and this will be housed in this sort of football stadium-like dome structure. So it will be absolutely enormous. But neither of these telescopes will be good enough to get the kind of images that I showed you just a minute ago. They're too small. We need larger telescopes. Trouble is, making large telescopes is very expensive, and at some point it becomes almost impossible to build a mirror that big. So we have to look for a different way. And the method we use is using arrays of telescopes, using lots and lots of smaller telescopes to build up a kind of patchwork kind of image of our objects. Now this is the ALMA array. This is in Chile in the Atacama Desert, and this is 66 radio telescopes up to 16 kilometers apart. And that means in effect, we can build up a 16-kilometer wide telescope just based off these much smaller single telescopes. And we can fill up the image by using the rotation of the Earth to produce a completer image as possible. And then we use software to fill in the rest of the image to create the kind of synthetic images I was showing you before. As well as radio observations, we also have infrared facilities. So this is the Very Large Telescope Interferometer. It's 2 sets of 4 telescopes. So you can, in effect, create a single telescope 130 meters wide. And then there's my favorite, because it's the one I work at and most of my data for my thesis is coming from, is the Chara Array, which is in California. This is 6 telescopes, which are up to 330, 340 meters apart, working in the infrared as well. And this observatory can produce some of the highest resolution observations on the planet. And it's just made up of 6 1-meter size telescopes. So far cheaper and far easier than building one telescope 330 meters wide. And it's using these techniques that we can build the images as I showed before. I realize I've talked a bit quicker than I expected, but yeah, this is my final slide. Yeah, so using these techniques, we can build the beautiful images that we saw before. So this is one of the original images taken using these techniques from several years ago now. This is how I thought the kind of images I would get for my PhD might look like. And then this is my actual image, which is a kind of blobby-like thing, but it's a result. So yeah, thank you for listening. And that's, yeah, a very brief overview of my PhD. So.